November 2nd, 1943, somewhere over the Bismarck Sea, 380 miles from Port Moresby. Second Lieutenant James B. Morehead felt the explosion before he heard it. His P-38 Lightning shuddered. The right engine screamed, belched black smoke, and died. Oil sprayed across the cowling. The propeller windmilled uselessly in the slickstream. No rescue ships, just water and the certainty that a single-engine fighter would be coming down. But Morehead wasn't flying a single-engine fighter. He was 23 years old. He had been in combat for 6 weeks. The mission had been straightforward on paper: escort B-25 bombers striking Japanese shipping near Rabaul, then return to base. Standard range, 800 miles round trip. Standard risk, everything. They had found the convoy, they had hit it hard, then Japanese Zeros had found them. In the chaos of turning, diving, firing, Morehead's wingman had called out the Zero, coming from his blind spot too late. The 20mm cannon round had torn through his right engine, nacelle like a fist through paper. Now he was alone, one engine, 380 miles of ocean, and a decision that would define whether he lived or died. The mathematics of survival were brutally simple. A P-38J Lightning weighed 17,500 pounds loaded. Each Allison V 1710 engine produced 1,040 T5 horsepower. Lose one engine and you lost exactly half your power. But you didn't lose half your weight, you didn't lose half your drag. The asymmetric thrust tried to yaw the aircraft into a spin. The dead propeller created drag equivalent to a barn door mounted on the wing, and single-engine service ceiling dropped from 44,000 feet to barely 20,000 feet on a good day. At combat weight, with ammunition expended and fuel burning down, maybe you could maintain altitude. Maybe. If you did everything perfectly. Morehead had never done this before. Not in combat, not over water. Not with his heart hammering and his hands shaking and the voice in his head screaming that he was going to die out here. But the training took over. Procedures drilled into him at Muroc Dry Lake in California, repeated until they became muscle memory. Feather the dead engine. Stop that propeller from windmilling. Reduce the drag. He reached for the feathering button, felt it click home, watched the propeller blades slowly rotate to their streamlined position. The vibration lessened. The yaw reduced. The Lightning stopped trying to kill him and started trying to fly. He trimmed the aircraft carefully, rolling in rudder trim to counteract the living engine's thrust. The P-38's counter-rotating propellers had been designed to eliminate torque effects in normal flight, but nothing about this was normal. His left leg ached from the constant pressure on the rudder pedal. He adjusted the trim tab again. Better. The Lightning steadied. He checked his instruments with the methodical precision of a man who knew that a single mistake would kill him. Airspeed, 18 miles per hour. Altitude, 18,000 feet. Fuel, enough, maybe, if he did everything right. The Lockheed P-38 Lightning had been born from an impossible requirement. In February 1937, the U.S. Army Air Corps had issued Specification X-618, demanding an interceptor that could reach 360 miles per hour at 20,000 feet and maintain that speed for at least 1 hour. The specification required a climb to 20,000 feet in 6 minutes. It required heavy armament. It required range that no single-engine fighter of the era could achieve. The Air Corps knew it was asking for something that didn't exist. They were asking anyway because the future was coming, and it demanded impossible things. Clarence Kelly, Johnson and the Lockheed design team looked at the requirements and realized immediately that no single engine could meet them. The math didn't work. To achieve that speed, that climb rate, that range, they would need approximately 2,000 horsepower. No single piston engine in America could produce that power reliably in 1937. But 2 engines could. 2 Allison V 1710 N-line engines, each producing roughly 1,000 horsepower, mounted in a configuration nobody had tried before: twin booms, central nacelle, tricycle landing gear, twin vertical stabilizers. It looked like something from science fiction. It looked like nothing else in the sky. The configuration solved problems and created new ones. Mounting the engines in wing nacelles instead of the fuselage meant the center pod could be devoted entirely to the pilot and armament. 4 .50 caliber machine guns and 1 20mm cannon, all mounted in the nose, all firing forward along the aircraft's center line. No convergence issues, no harmonization problems. The guns pointed where the nose pointed. At 1,000 yards, the bullets went exactly where you aimed them. Single-engine fighters had their guns mounted in the wings, angled inward to converge at perhaps 300 yards. Miss that convergence point and your fire spread uselessly. The P-38's central armament was devastating at any range, but twin engines meant complexity. 2 engines to maintain. 2 sets of superchargers, intercoolers, oil systems, cooling systems, 2 engines to fail. And when one failed, the asymmetric thrust created handling problems that could kill inexperienced pilots. During takeoff and landing, when speed was low and control authority was minimal, losing an engine meant immediate disaster if the pilot couldn't react instantly. The torque would flick the aircraft into the ground before you could even process what was happening. Training losses were significant. Pilots died learning the Lightning's characteristics. The aircraft gained a reputation as a widowmaker among some training squadrons, yet the pilots who mastered it discovered something remarkable. The P-38 was honest. It demanded precision, but if you gave it precision, it rewarded you with capabilities no other fighter possessed. The counter-rotating propellers eliminated torque effects in normal flight. The tricycle landing gear made takeoffs and landings straightforward compared to tail-dragging fighters that required constant attention to prevent ground loops. The cockpit was spacious, the visibility was excellent, and the range was extraordinary. Morehead held his course, southwest, toward Port Moresby, toward safety. He ran the calculations in his head. Distance remaining, approximately 340 miles. Speed, 180 miles per hour. Time to base, just under 2 hours. Fuel consumption on one engine, at this power setting, at this altitude. He didn't know exactly, but he knew it would be close. The Allison V5-1710 engine consumed roughly 70 gallons per hour at cruise power. He was running higher than cruise power because he needed to maintain altitude and airspeed, maybe 90 gallons per hour, maybe more. He had perhaps 200 gallons remaining in his internal tanks. The drop tanks were gone, jettisoned during the fight. The math was brutal, but not impossible. 2 hours alone over the Bismarck Sea, 2 hours with nothing below but water and sharks. The Pacific theater was defined by distance. From Port Moresby to Rabaul was over 600 miles. From Guadalcanal to Bougainville was 400 miles. The distances made the European theater look compressed, intimate. In Europe, you were never more than 200 miles from friendly territory. In the Pacific, you could be 800 miles from anything. The vastness changed everything. It changed tactics. It changed aircraft selection. It changed what pilots feared. In a single-engine fighter over the Pacific, engine failure meant death. You could bail out, assuming you survived the bailout, assuming your parachute opened, assuming you didn't break your back hitting the water. Then you were in the water, in the tropics, with no rescue possible for hours or days. Sharks arrived quickly in these waters. Pilots knew this. They had seen the sharks from altitude, dark shapes cruising beneath the surface. General George Kenney, commander of the 5th Air Force, had famously said he wanted P-38s in the Pacific precisely because you look down from the cockpit and you can see schools of sharks swimming around. The twin engines meant survival. They meant you could lose an engine and still come home. But it had never been tested like this. Not at this distance, not this far from base. Small engine failures over shorter distances, yes. Pilots had limped home 50 miles, 100 miles on one engine, but 340 miles over water. Nobody Morehead knew had tried it. He monitored his instruments with obsessive attention. Oil pressure on the good engine, normal. Cylinder head temperature, rising slightly but within limits. He adjusted the mixture, leaned it out carefully to conserve fuel. Too lean and the engine would overheat, seize, kill him. Too rich and he would run out of fuel 50 miles from base, ditch in the ocean, die anyway. The margin between survival and death was measured in precise adjustments of the mixture control. He touched it delicately, feeling for the sweet spot where the engine ran smoothly but efficiently. The Lightning had been designed with brutal honesty about the realities of long-range flight. The twin-boom configuration wasn't just aesthetically distinctive, it was functionally necessary. Placing the engines in the booms, away from the fuselage, meant that engine fires were less likely to engulf the pilot. It meant that battle damage to one engine didn't automatically cripple the entire aircraft. It meant redundancy. The turbo superchargers, mounted behind each engine, gave the Lightning its high-altitude performance. They compressed the thin air at altitude, forcing it into the engine at sea-level pressure, maintaining power where other fighters gasped and struggled. At 18,000 feet, the air pressure was roughly half that at sea level. A naturally aspirated engine would produce half its rated power. But the turbo-supercharger compensated, compressed, delivered air as if the aircraft were flying at 5,000 feet. The result was an aircraft that could fight effectively at 35,000 feet, higher than Japanese fighters could operate, higher than most German fighters wanted to engage. Altitude was energy. Altitude was life. The Lightning climbed to altitude quickly and fought from above. Morehead's altimeter read 17,800 feet now. He was descending slowly. The single engine couldn't quite maintain 18,000 feet at this weight, this configuration, this power setting. He considered increasing power but rejected it. Better to descend gradually and conserve fuel than to burn extra fuel maintaining altitude. At 15,000 feet he would still be high enough. He watched the altimeter. 17,600 feet, 17,400 feet. The descent was gentle, almost imperceptible, but relentless. Time compressed and expanded strangely. Minutes felt like hours. He checked his watch. 20 minutes since the engine failed. It felt like a lifetime. It felt like seconds. He forced himself to breathe slowly, deliberately. Panic would kill him as surely as fuel starvation. He thought about his training. The long hours at Muroc, learning the P-38 systems, learning its handling characteristics, learning what it could and couldn't do. His instructor had been emphatic. The Lightning will take care of you if you take care of it, but it demands respect, it demands precision. Get sloppy and it will kill you. He was not being sloppy. Every control input was deliberate, measured, precise. The Lightning responded predictably. The asymmetric thrust was manageable with proper trim. The single engine ran smoothly. The aircraft flew. It was wounded, but it flew. That was the revelation. That was what separated the P-38 from every single engine fighter in the theater. It could be wounded and still fly. It could lose half its power and still bring its pilot home. The implications of this capability rippled through 5th Air Force operations. Pilots flying P-38s into combat over water approached the mission differently than pilots in P-40s or P-39s. The psychological difference was profound. In a single-engine fighter, you were constantly aware that mechanical failure meant death. In a P-38, mechanical failure meant inconvenience, effort, careful flying, but not automatic death. This changed how aggressively pilots engaged. It changed how far from base they were willing to fight. It changed the calculus of risk. He had been flying P-39 Airacobras and P-40 Warhawks, adequate fighters, but limited in range and increasingly outclassed by improved Japanese fighters. The P-38 changed everything. Its range exceeded 2,000 miles on internal fuel. With drop tanks, it could fly 1,500 miles, 1,800 miles, missions that were simply impossible for single-engine fighters. The long range meant Allied fighters could suddenly appear over Japanese bases that had been considered safely distant. It meant escort missions could protect bombers all the way to target and all the way back. It meant air superiority could be projected hundreds of miles from base. On December 27, 1942, 12 P-38s of the 39th Fighter Squadron, newly arrived at Port Moresby, intercepted a Japanese formation of 25 fighters and dive bombers. The P-38 pilots claimed 11 kills. 1 Lightning was lost. The exchange ratio was stunning. More importantly, the psychological impact was immediate. The Japanese had owned the skies over New Guinea. Suddenly, they didn't. The P-38, with its speed, its firepower, its ability to fight at altitude where Japanese fighters struggled, had shifted the balance. Morehead checked his fuel gauge. 140 gallons remaining. Distance to base, maybe 200 miles. The math was getting tighter. He recalculated. At 90 gallons per hour, he had 90 minutes of fuel. At 150 miles per hour, 90 minutes gave him 270 miles of range. That left a 10-mile margin. 10 miles. The margin between life and death was 10 miles and shrinking. He considered his options. He could increase speed, get home faster, but that would increase fuel consumption proportionally. No gain. He could reduce speed, decrease fuel consumption, but he was already at the edge of single-engine performance. Slower, and he would start descending faster. The Lightning was heavy, even with fuel burning down and ammunition expended. He was flying at the ragged edge of the aircraft's single-engine capability. There was no margin for error. The engineering that made this possible was remarkable in its elegance and its complexity. The Allison V1710 engine was a liquid-cooled V112, each cylinder precisely machined, each component balanced, the entire assembly designed for sustained high-output operation. The engine displaced 1,710 cubic inches, hence the designation. At war emergency power, it produced 1,425 horsepower while screaming at 3,000 RPM. The cooling system circulated ethylene glycol through passages in the engine block and cylinder heads, absorbing heat, routing it to radiators mounted in the wing leading edges and chin scoops, dissipating it into the airstream. Lose the cooling system and the engine would seize in minutes. The glycol temperatures had to be maintained within narrow limits. Too cold and the engine couldn't develop full power. Too hot and metal components would warp, seize, fail catastrophically. Morehead watched his coolant temperature gauge, 80 degrees Celsius, normal. The system was working. The good engine was carrying him home. The propeller was a miracle of metallurgy and engineering. Curtiss electric propellers, each blade a precisely shaped airfoil, each blade adjustable in pitch through a complex electromechanical system. At high speed, the blades could be set to fine pitch, taking small bites of air, allowing the engine to rev freely. At low speed, the blades rotated to coarse pitch, taking large bites of air, generating thrust efficiently. And when an engine failed, the blades could be feathered rotated edge onto the airstream, minimizing drag. The feathering system was the difference between gliding home and spinning into the ocean. Morehead had feathered his dead engine immediately. It was the first critical step. Leave the propeller windmilling and the drag would be enormous, potentially uncontrollable. The windmilling propeller would create drag, equivalent to multiple times the normal engine-off drag. The aircraft would descend rapidly, possibly uncontrollably. Feathering stopped the propeller, streamlined it, made single-engine flight possible. He was over halfway home now, 180 miles remaining, 100 gallons of fuel. The math was becoming survivable. He allowed himself to believe, briefly, that he might actually make it. The P-38's design had been vindicated in the Pacific in ways its designers hadn't fully anticipated. Kelly Johnson and the Lockheed team had designed it to meet Air Corps specifications for speed and altitude. They had designed it for interceptor missions over the continental United States, or perhaps bomber escort over Europe. They had not specifically designed it for 1,000-mile missions over tropical oceans against Japanese fighters. But the fundamental capabilities they had engineered into the aircraft range, twin-engine reliability, high-altitude performance, heavy firepower, proved perfectly suited to the Pacific theater. The aircraft's distinctive appearance made it immediately recognizable. The twin booms, the central nacelle, the twin vertical stabilizers created a silhouette unlike anything else in the sky. Pilots called it the fork-tailed devil. Japanese pilots called it two planes, one pilot, because the twin booms looked like two aircraft flying in formation. The sound was distinctive too. The twin Allison engines, slightly out of synchronization, created a rumbling, throbbing note that pilots on the ground could identify instantly. When you heard that sound, you knew Lightnings were overhead. The nose armament gave the P-38 a killing power that was almost unfair. The 450 caliber machine guns, mounted two above and two below the 20mm cannon, converged in a tight pattern directly ahead of the aircraft. The combined rate of fire was approximately 650 rounds per minute from the machine guns, 600 rounds per minute from the cannon. In a 2-second burst, a P-38 pilot could put nearly 50 rounds into a target. The 050 caliber rounds could penetrate Japanese aircraft easily. The 20mm cannon rounds exploded on impact, tearing apart control surfaces, fuel tanks, engines. Japanese aircraft were lightly built, optimized for maneuverability over protection. American ace Richard Bong, who would become the top American ace of World War II with 40 victories, flew only the P-38. He preferred it over every other fighter. In his hands, the Lightning's capabilities were fully realized. He understood how to use the aircraft's strengths, speed, firepower, altitude performance, while avoiding situations where its weaknesses, low-speed maneuverability, roll rate at high speed, would be exposed. He flew with methodical precision. He stalked his targets, positioned himself advantageously, attacked from altitude with surprise, used the Lightning's speed to disengage before Japanese fighters could respond. He survived the war. Thomas Maguire, the second highest American ace with 38 victories, also flew the P-38 exclusively. He was more aggressive than Bong, more willing to engage in turning fights, more willing to push the Lightning to its limits. He died in combat in January 1945, killed when his P-38 stalled at low altitude during a violent evasive maneuver. The Lightning's limits, when exceeded, were unforgiving. Morehead was not an ace. He was a competent pilot, careful, precise, not particularly gifted but thoroughly trained. Today, that training was saving his life. The navigation was entirely by dead reckoning, no GPS, no radio navigation aids, just compass, airspeed, time and calculation. He had set his course southwest toward where Port Moresby should be, but wind was pushing him. Winds at altitude in the tropics were unpredictable. He might be 20 miles south, of course. He might be 20 miles north. He wouldn't know until he saw land or didn't. Miss Port Moresby, and he would fly out over the Coral Sea, run out of fuel, ditch, die. The pressure was enormous, but he couldn't let it affect his flying. Panic killed pilots. At 120 miles from base, he began his descent. He needed to conserve altitude for the approach, but he also needed to reduce power gradually as his fuel burned down. The descent would be slow, controlled, a gentle glide toward home. He reduced power slightly, the nose dropped, airspeed held steady. He was descending at 200 feet per minute. At 15,000 feet now, he would reach 5,000 feet right around the time he should be over Port Moresby. If his navigation was correct, if the winds hadn't pushed him too far off course, if... The Lightning's handling characteristics changed subtly as fuel burned down and weight decreased. The aircraft became more responsive, more willing to accelerate, more willing to climb. But on one engine, at reduced power, the improvement was marginal. He was still fighting to maintain altitude, still bleeding height slowly despite his best efforts. At 80 miles out, he was at 11,000 feet. The descent was inexorable. Charles Lindbergh had visited the Pacific Theater in 1944, ostensibly as a civilian technical representative for United Aircraft, actually as a highly experienced pilot who wanted to understand combat operations. He was forbidden by the Roosevelt administration from officially returning to military service due to his pre-war isolationist stance. But in the Pacific, far from Washington, he flew combat missions anyway. He flew P-38s with several squadrons, teaching pilots the cruise control techniques he had perfected during his 1927 Atlantic crossing. Lean the mixture, reduce RPM, optimize altitude for fuel efficiency. The techniques extended the P-38's range dramatically, from 1,200 miles to potentially 1,500 miles, 1,800 miles on a single tank of fuel plus drop tanks. The pilots loved him. Here was the most famous aviator in the world, the Lone Eagle, flying combat missions with them, sharing hard-won knowledge about how to stretch fuel to impossible distances. On July 28, 1944, Lindbergh shot down a Japanese fighter while flying with the 475th Fighter Group. He was 52 years old. The kill was never officially credited because he was a civilian. Nobody cared about the paperwork. The pilots knew. Morehead had learned Lindbergh's techniques. He was flying them now. Mixture leaned to the edge of rough running. RPM reduced to minimize engine stress and fuel consumption. Altitude optimized for maximum range. Every technique Lindbergh had taught was being employed. Without those techniques, he would already be out of fuel, in the water, dying. At 60 miles out, his fuel gauge read 40 gallons. He was going to make it. The realization came slowly, carefully, without celebration. He was going to make it. The Lightning had carried him 320 miles on one engine. It had done what single-engine fighters couldn't do. It had brought him home. At 40 miles out, he saw the coast of New Guinea. The sight was overwhelming. Land, safety. He descended toward Port Moresby, the good engine running smoothly, the aircraft responding precisely to his inputs. He contacted the tower, explained his situation, was cleared for immediate landing. He configured the aircraft for approach, flaps down, landing gear down, airspeed 120 miles per hour. The single engine carried him across the threshold, over the runway, into the flare. He touched down gently, rolled out, taxied to the parking area. When he shut down the engine, the silence was profound. He sat in the cockpit for a long moment, hands shaking, breathing hard. He had flown for 2 hours and 40 minutes on one engine. He had covered 380 miles over open ocean with half his power plant dead. He had survived because Lockheed engineers in Burbank, California, had designed an aircraft with redundancy, with twin engines, with the capability to absorb damage and keep flying. The ground crew swarmed the aircraft. They examined the dead engine, whistled at the damage. The 20mm round had destroyed the intercooler, severed oil lines, shattered the reduction gear housing. The engine was completely destroyed. "How'd you get home on one engine?" the crew chief asked. Morehead looked at him. "I flew carefully," he said. The story spread through the squadron, then through the group, then through 5th Air Force. Lieutenant Morehead flew 380 miles on one engine and made it home. The story was important not because it was unique. Other pilots had made similar flights, shorter distances but similarly desperate, but because it demonstrated empirically what pilots had believed theoretically. The P-38 could take catastrophic damage and still fly. The twin engines weren't just a design feature, they were a lifeline. The psychological impact on P-38 pilots throughout the Pacific theater was immediate and profound. Pilots approached missions over water with confidence they hadn't felt in single-engine fighters. The confidence translated into aggressive tactics, longer-range missions, willingness to engage enemy fighters far from base. The Japanese, already struggling with trained pilot losses and fuel shortages, found themselves facing opponents who seemed everywhere, who appeared over formerly safe bases, who fought with technical superiority and psychological confidence. By late 1943, the P-38 had become the dominant fighter in the Southwest Pacific. The 475th Fighter Group, flying P-38s exclusively, produced more aces than any other Army Air Force group in the theater. The 49th Fighter Group, partially equipped with P-38s, contributed significantly to air superiority over New Guinea and the Philippines. The aircraft's combination of range, firepower, speed, and twin-engine survivability made it ideal for Pacific operations. The twin-engine configuration that had seemed like a liability during training, more complex, more maintenance-intensive, harder to master, proved to be the critical advantage in combat. Pilots who had worried about the complexity discovered that the complexity brought them survival. Two engines meant redundancy. Redundancy meant coming home. Coming home meant fighting another day. The P-38 service in the Pacific ultimately destroyed more Japanese aircraft than any other American fighter. The total exceeded 1,800 confirmed kills. 7 of the top 8 American aces flew P-38s. The aircraft operated in every Pacific theater: Southwest Pacific, Central Pacific, China, Burma, India, Aleutian Islands. It flew the longest-range fighter missions of the war, including a 10.5-hour mission in early 1945 covering over 2,000 miles. It participated in the single most famous fighter mission of the war, the April 18, 1943, interception of Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack. Only the P-38 had the range and speed to fly 435 miles from Guadalcanal, intercept Yamamoto's bomber transport, and return. The engineering decisions made by Kelly Johnson and the Lockheed team in 1937, twin engines, turbo superchargers, tricycle landing gear, central armament, had created an aircraft uniquely suited to Pacific operations. They had not known the Pacific War was coming. They had designed to specifications. But the specifications had demanded capabilities that proved exactly right for the war that would be fought. Morehead flew 23 more combat missions. He damaged his P-38 twice more, once from ground fire, once from a Zero's deflection shot that holed his wing but missed everything critical. He never had to fly home on one engine again. But he knew he could. Every P-38 pilot in the Pacific knew they could. That knowledge changed everything. In the broader scope of aviation history and military operations, the P-38's twin-engine survivability represented a fundamental insight about design philosophy. Single-engine fighters were simpler, lighter, cheaper, easier to maintain. The twin-engine fighters offered redundancy at the cost of complexity. In the European theater, where distances were short and emergency landing fields were common, the trade-off favored single-engine fighters. The P-51 Mustang, with its superb range and performance, ultimately replaced the P-38 in Europe. But in the Pacific theater, where distances were vast and emergency landing fields consisted of shark-infested ocean, the trade-off decisively favored twin-engine designs. The complexity was worth it, the redundancy was essential. The capability to fly 380 miles on one engine was the difference between life and death. It applied to any system operating in unforgiving environments where failure meant catastrophe. Redundancy costs money, weight, complexity, but redundancy buys survival. The P-38 embodied this principle completely. Its pilots understood it intimately. They trusted the Lightning to bring them home because it had the capability to survive damage that would destroy other aircraft. Morehead was awarded the Distinguished Flying Cross for his flight. The citation mentioned his skill and determination in bringing a damaged aircraft home over 380 miles of open ocean. It didn't mention the engineering that made the flight possible. It didn't mention the turbo superchargers, the feathering propellers, the twin Allison engines, the redundant systems. But those systems were the foundation of his survival. Without them, skill and determination would have been irrelevant. He would have been another name on the casualty lists, another pilot lost over the Pacific. The P-38 served throughout the war and was retired shortly after. The jet age was beginning. Piston engine fighters, no matter how capable, were becoming obsolete. The P-80 Shooting Star, America's first operational jet fighter, was faster, simpler, more capable. Ironically, Richard Bong, the top American ace, was killed test flying a P-80 on August 6, 1945, the same day the atomic bomb fell on Hiroshima. The war was ending. A new era was beginning. In hostile environments, redundancy enables survival. Twin engines meant pilots could lose an engine and still come home. The principle applies to spacecraft, to aircraft, to any system where failure is not acceptable. The engineers who designed the Apollo spacecraft put redundancy into every critical system, precisely because they understood what the P-38 pilots had learned over the Pacific. When you're far from home and help is impossible, redundancy is the only thing standing between you and death. Morehead survived the war. He returned to Iowa, became an agricultural engineer, designed irrigation systems. He never spoke much about the war, but he kept a photograph of his P-38 on his desk for the rest of his life. The photograph showed the Lightning on the ground at Port Moresby, one engine clearly damaged, propeller feathered. Someone had written on the back, "She brought me home." That was the P-38's legacy in the Pacific. It brought pilots home. It gave them a chance when chance should have been impossible. It translated engineering excellence into pilot survival, transforming the mathematics of twin-engine flight into the reality of men living to fight another day. In a war where so many didn't come home, the Lightning's ability to absorb catastrophic damage and continue flying was more than a technical achievement. It was a lifeline. It was hope. It was the difference between a name on a memorial and a man walking off the flight line, shaking, exhausted, alive.